In the lecture, guys. So, surface integrals. Let's choose a new color. What color should we go for? Blue. But we've been doing blue. But I must admit, we don't do a lot of purple, do we? Let's do purple. Here we go. Surface integrals. Okay. Please keep quiet. Please keep quiet. Okay. Surface integrals, right. So surface integrals they look superficially similar to double integrals because they also have two integral signs. Oh, excuse me. Fogging my throat this morning. But they are what's the word here? Substantively different from double integrals because the region over which we're integrating is not a two-dimensional region on the xy plane. It's not a flat lamina. It is a piece of surface floating in three-dimensional space. So it's a double integral in the sense that it's got two integral signs, but the thing that you're integrating over is a three-dimensional object. Could you please put your phones away? So the rough technique that we're going to use when we do surface integrals is we're going to take our piece of surface and we're going to take our surface integral and we're going to turn it into a double integral by projecting our piece of surface onto one of the coordinate planes to almost like cast a shadow onto one of the coordinate planes, and it's that shadow, that projection, that we're going to be using as our region over which our double integral will be integrated. Okay, so we're going to turn surface integrals into double integrals, and then we're going to actually carry out the integration calculation. And it's that turning a surface integral into a double integral which is where all of the tricky bits come in. Okay, so first of all, I'm going to derive the conversion factor. I'm going to derive the expression that the factor that we're going to have to use when we do that projection. All right, so a little bit of writing. Suppose that a surface S in R3 is part of a graph, in other words, part of a surface of a function z equals f of xy. Okay, so we've got z equals f of xy, which describes a paraboloid, a sphere, a plane, whatever. And we're going to take a piece of that, and we're going to call that piece S. If we divide S into small rectangles, of area delta S, we can find the area of S, which we would write like that, and is basically a double sum, well, it's a limit of a double sum, so let me write the limit in. Okay, I'm being sloppy there. I'm not putting in any of my little things written underneath it. But basically what's going on is exactly what went on with double integrals. We take our surface, we chop it up into lots of little rectangles, and each little rectangle has an area. And then what that double sigma is it's adding up all of the areas to get the total area. Or we can work out mass of S, which would be mass is... I don't know whether that's particularly clear. The thing that I'm writing at the bottom of those two integral signs is an S. Very similar to our double integral, but instead of a dA we have a ds because each little rectangle is a little piece of S. And my density is a function of three variables because my surface is floating in space, and the density at any one point could be a function of that three-dimensional point in space. Okay, so those are the sorts of calculations that we're going to be solving. And on the surface, that looks great because you can just write integral 1 ds. Yay, let's jump into integrating. But we can't jump into integrating because there's a key difference between this kind of integral and the dA integrals, the dA integrals we had before with the double integrals. Because dA was a little piece of area where we pictured the rectangle as being a rectangle lying flat in the xy plane, and we could say that delta A was delta x times delta y, length times breadth of the rectangle. And so we could break that dA in the integral up into dx dy, and then we could actually do an x integral and we could do a y integral. We can't do that with delta S, because delta S is not a little rectangle that's lying flat on the xy plane, or flat on the xz plane, or flat on the yz plane. So we can't describe that delta area. I mean, it's still length times breadth, but the length and the breadth are not easily described in terms of delta x or delta y or delta z. So how are we going to take the integrals as they look here, which is perfectly fine? Those are beautiful, lovely integrals. But how are we going to turn them into integrals so we can actually calculate? That's the trick. Okay, so to write that down in a sentence, the trouble is that delta S is not equal to delta X, delta Y, or delta X, delta Z, or delta Y, delta Z, because delta S is a little piece of rectangle floating in space. Okay. We need to transform our delta S into something which we can express as delta X, delta Y. Or delta Y, delta Z, or delta X, delta Z, but basically D variable, D variable. Or similar. So that we can actually integrate. We can actually carry out a calculation. Okay, so how are we going to do that? We're going to do that by taking our surface and projecting it onto one of the coordinate planes. It could be any of the coordinate planes, but it frequently is xy. It's frequently the xy plane, but it could be any of them. Okay, so the first thing we're going to do is we're going to project S onto a coordinate plane, frequently xy, but not necessarily. Frequently xy, but not necessarily. And we'll call the projection R. Okay, so a picture, I'm going to draw a picture. Let's say we have some surface in space, some curvy surface in space, and when I project it down onto the xy plane, I get my projection. So this is my S, and this is my R down on the xy plane. It could be a different coordinate plane. It doesn't have to be xy. So I'll be talking about xy all the time, but it could be any of them. And when we get to the end of this whole section, I'll show you how, if you've chosen one of the other coordinate planes, the expression that you get would look slightly different. Okay, and then if we just draw R, it'll be like this. Okay, so there's R. Okay, and let me take, let's have a look. A rectangle in delta R and its corresponding rectangle on delta S. Let's have a look. Here's my rectangle down there in R, and I'm deliberately trying to draw something that looks kind of curvy up there on the surface. Okay, so that's the rectangle on S that when you project down onto the xy plane would form that red rectangle in R. And I'm very deliberately drawing the rectangle in R parallel to the x and y axes. Okay, so I've got the little projection there. There's my delta S down here. There's my little delta A rather. Okay. I'm locating my little red rectangle in my projection. I'm locating it at some mystery xk, yk. And my length is delta x and my breadth is delta y. Okay, all right. What was I at? Purple. Okay. So each delta S rectangle, I'm saying rectangle, but it's a piece of surface, so it'll be a little bendy rectangle, a little curvy rectangle. It won't be flat. Each delta S projects onto a delta A in R, okay? An important issue, and this is what I was talking about, was it yesterday? No, I think it was the day before, when I was holding my book out and I was talking about the projection. If my book was casting a shadow on the ground, the shadow of, if my book is tilted, the shadow of the book will not be the same area as my actual book, but they will be related. And that's very important. My delta S and my delta A are not equal, but they are related to one another. An important issue is that the area of delta S, which is what we're really interested in, is not equal to the area of delta A. But these areas are definitely related. Okay, so let's think about my book again. If I hold out my book, let me take my handbook. If I hold my book out, okay, like this, and it's a rectangle, it's got a certain area, and I shine a very sharp light on it, so point source infinitely far away light, and it casts a nice sharp shadow on the ground. The shadow of my book will not be the same area as the actual area of my book, but they will be related. Because if I keep the slope constant, but I make the book bigger, the shadow will also get bigger. If I keep the area the same, but I change the tilt, the shadow will also change size. So my delta A, which is the shadow down on the ground, is related to my delta S in both the actual magnitude of delta S and the magnitude of delta A are related, like the actual area, but also the tilt. In other words, what the function is doing. If delta S if my delta S book here was a piece of a function, then where the function is steeper or where the function is shallower is going to make a difference to how big the projection is. So what we're going to end up with is delta S being equal to delta A times by a conversion factor, where that conversion factor is a function of, well, it is in terms of the function that's describing the surface that delta S is a part of, because the characteristics of that surface are going to affect the projection. Okay, but I'll derive it all. These areas are definitely related. I put a full stop, but I don't want a full stop. And we can express that relationship with what you could call a scaling factor, or perhaps a conversion factor. Okay, so what we're going to end up with, we're going to end up with delta S, which is what we're starting with. We've got an integral that's got a ds in it, which is all fine and well, but it's useless for actual calculation purposes. So we're going to turn it into some conversion factor times by delta A. Because the relationship between delta A and delta S can be expressed with this conversion factor, and the conversion factor itself is going to depend on the function that's describing the surface that delta S is a part of. Okay, so now the job ahead of us now is to find that conversion factor. Hopefully it seems reasonable. Hopefully what I've said so far is reasonable. It sounds acceptable that delta S and delta A are related by means of some sort of factor. But what is that factor? Okay, alrighty then. So what I'm going to do is I'm going to approximate delta S with its tangent plane. Okay, so now we're going to have three rectangles in our picture. We're going to have the rectangle delta A, which is lying on the XY plane. We're going to have our curvy rectangle delta S, which is on the surface. And then we're going to have the little mini rectangular plane that's an approximation of delta S. So delta S and what I'm going to call delta T will be very similar to one another, but delta S is curvy and delta T is not. Delta T is a linear approximation of delta S. And of course, the smaller delta S gets, the closer delta T and delta S are going to be to one another. Okay, so we approximate. And why am I going to do that? Because we know that we can describe the area of a parallelogram using the cross product of vectors. Don't we? We know that. Yes, we know that we can express the area of a parallelogram using the cross product of vectors. So we're going to describe the area of that little piece of tangent plane using the cross product of vectors, where those vectors have delta x and delta y in them. And that's how we're going to jump from delta S to delta A. Okay, everybody had their coffee this morning. You all had your Pronutro? You all had your wheat bix with extra sugar? Yay! We approximate delta S with its tangent plane. Okay, I'm going to draw a picture to back this up, but first I'm doing some writing. As delta S tends to 0, the approximation becomes not an approximation anymore, it becomes a perfect fit. Please keep quiet. You're going to need to concentrate here. Please keep quiet. This is useful, as each delta T is a parallelogram. Well, it is a rectangle, but rectangles are parallelograms. And we can express the sides of the parallelogram, which I'm writing as that symbol over there. I hope you recognize that symbol, as vectors. Do you ever use that symbol at school? Two parallel sides with a little superscript M. It's an abbreviation for the word parallelogram. Okay, well now you've seen it. Yay, you've learned something new, even over and above surface integrals. It's a good day. And it's not even 20 past 8. Wow. Okay, and we can express the sides of the parallelogram as vectors involving delta x and delta y, and determine the area of the little delta tk parallelogram using the cross product. It's like ninja maths. Here we go. Okay, all right. Phew. So I know that's a lot of writing, and you're all diligently copying it down, and what am I doing? I'm just scrolling. So let me pause for a second while people catch up. I'm now going to draw a picture. I'm going to draw a nice big picture. It's going to have 3 rectangles on it. It's going to have a delta A, a delta S, and a delta T. And the delta T is going to have little vectors as its sides, and those little vectors are going to have delta X's and delta Y's. And then we're going to jump into a cross product, and then we're going to be at the end. Ta-da! Yes?
Could you explain why we wouldn't have rectangles or squares for delta T? Like, I don't understand.
Delta T is a rectangle. But a rectangle is a special case of a parallelogram.
Right.
Yeah.
Okay, so we're not talking about skew parallelogram.
No. Okay, all right. Let's go on to the pretty picture. Although it's actually quite a big picture. How much space do I have left on this virtual page? Very little. I want to do a page jump.
Go.
So who was here last night for the UCT Maths competition? Did you see it? Wasn't it awesome? Who used to do the UCT Maths competition when you were in high school? Show hands. Yay, Cape Townians. The UCT mathematics competition is the largest maths competition in the world to be held at a single venue. There are larger maths competitions just like participation-wise, but they tend to be like split across cities or something like that. Over 8,000 high schoolers were enrolled to do it. We never get everybody's. There's always only about 90% participation rate. So it possibly wasn't quite as many as 8,000 who were here last night, but there were approximately 8,000 high school students, learners, whatever they're called, scholars, from all over Cape Town and the environment. They bus in from Bredasdorp, they come down from Namaqualand, and it's incredibly exciting, and I've been involved with it for many years. If you've written the UCT Maths competition, you've probably written some papers I've helped set. I helped set the grade 8 one this year. Yeah? Okay, can we jump page now? Yeah.
Are we using the cross product instead of just multiplying x and dx by y because it might be skewed?
Well, the thing is, it's going to be skew insofar as it's not going to be necessarily horizontal. Okay, let me draw a picture. I think everybody's caught up now. There'll be, yes.
Okay.
Yes. Okay, so here's the picture. All right, let me get this picture. So I'm drawing it nice and big. Here's my delta A. Please keep quiet. Please keep quiet. Okay, That's pretty useless. There we go. There's my delta S. This dotted thing is my delta S. It's the actual piece of surface that we're really interested in. But it's kind of elusive when we try to describe it in ways that we can actually do calculations. Here's delta T, which is its tangent approximation. Okay, so it's its linear approximation. So picture a point right in the middle of delta S. You're working out the tangent plane at that point, and then you're just taking the little bit that's actually a direct match to that rectangular bit of delta S. Okay, and here's my delta A down at the bottom. I'm just giving them a subscript K because they're being numbered. But basically delta S, delta T, delta A. And I'm going to describe the sides of my rectangle. Let's have a look. If I'm drawing it that way, I'm probably wanting to do that. Okay. So delta T, I'm going to work out the area of delta T. And I'm going to work it out using the cross product of vectors, where those vectors describe the length and the breadth of the rectangle. Okay, all right, here we go. So U, the way I've drawn it, U is varying with respect to X, not with respect to Y, but of course it will be with respect to Z because that's the whole point. This is a tilted rectangle floating in space. Yes?
What do you mean not with respect to Y?
I've deliberately chosen that down here is my projection of delta X. Of U. U projected. And over here, this is my V projected. And I've deliberately designed it that way. You could make it so that those vectors are not parallel to the coordinate planes, and you could still do this calculation. It would just be messier. And we have the power to design this how we want, so that's how I've done it. Okay, lovely, great. Everybody happy? Okay. But we don't really want a delta Z hanging around, so I want to describe delta Z in terms of the things I really want, which are delta X and delta Y. Okay, now what I'm doing there is a thing that I've done several times already in different contexts. Here's delta Z, Here's delta x. Here is the slope delta z. Well, this horizontal, that hypotenuse has a slope of delta z over delta x. Therefore, delta z is equal to delta x times the slope. So it's equal to delta x times the x derivative. Okay, this is at least the third time we've seen this idea, how you can work out delta something in terms of delta something else by linking them with the slope. Okay, the slope of, if you draw a little rise over run, the slope is rise over run, and therefore rise is equal to run times slope. Okay, where the slope in this case is the x derivative. Okay, this may be something that you'd think, gosh, if I had to do this by myself, I wouldn't get it right, and that's okay, but I hope that you're following it given that I'm presenting it, which is a different thing. And then my v vector is very similar. Now the x isn't changing, the y is, and I similarly have a delta times a slope, but it's delta y, and it's the x slope. Okay. Area of delta tk is equal to the modulus of u crossed with v. And you would have done that in first year vector geometry. If you go dig through your notes, you'll find it there somewhere. So you can take u and v and you can cross them. Okay? So three-component vector, carry out your cross product, and you'll get a rather messy thing. In fact, I tell you what, let me write it underneath because it's so wide. But don't worry, it simplifies. But if at first, when you first do your cross product, this is what you get. You get a negative delta x, delta y, x derivative. You get a negative delta x, delta y, y derivative, and you get a delta x, delta y. You can carry out your cross product. It's just a cross product. It's just a rather chunky cross product because all the bits are so big. But it's just a cross product. How many cross products have you done in your life? Hundreds. Do I want to write equals at this stage? Not really. What I want to write is this. I want him to work out the modulus of that. Oh my goodness, that's going to be a huge big mess. Yes, it is, but then it tidies up very nicely. Okay, we're going to square. We're going to work out the sum of the squares of the components. But notice how every single component has a delta x and a delta y in it. So when you square them, they're all going to have a delta x squared, a delta y squared. You can take that out as a common factor and you can pull it out at the square root. Can I skip some steps? There were yeses and nos. I won't skip steps. Yeah. If you don't mind, I'm just going to write f sub x and leave out the... Can we just assume that? Yeah. Okay, to just save some symbol space on the page. Little bit sloppy and shouldn't really be sloppy. There we go, there's the modulus. I'm going to take that delta x, delta y out as a common factor, and I'm going to pull it out of the square root, which means it stops being squared. So it becomes, I'm going to put it at the end, so it'll be fx squared plus fy squared plus 1 delta x, delta y. Normally we actually write the 1 first, but I'm just keeping them in the order that they've come out here. What's the bottom line? Bottom line is that in the limit, as number of delta s subdivisions tends to infinity, and they become infinitesimally small, infinitesimally infinitesimally, have I spelled that right? Have I put in too many vowels? Who knows? Infinitesimally small. And delta t and delta s essentially become closer and closer to one another. ds, notice I'm using a d now because it's in the limit. 1 plus the x derivative squared plus the y derivative squared dA, where dA of course is dx dy.
Do you not need an integral sign?
I'm not integrating anything yet. I could put an integral sign, sure, and then I'd put one on each side. In fact, I'd have to put two on each side. I'm simply showing how you turn your ds into dA. Question? Yes, but it means very small, but it's used in the context of very small. Excellent word. Try and use it at least 3 times before nightfall. A casual conversation. These portions at res are becoming infinitesimally small. So yeah, I managed to think of one just off the top of my head. I'm sure with your creativity you can come up with at least 2 more. And that's what we do. So if you've got a surface integral always has a d big S at the end, then that's beautiful and lovely and fabulous, and you can frame it and put it on your wall, but you cannot actually solve it as an integral until you change the ds into dA. Because only after you've changed ds into dA with the help of that conversion factor, only then can you break dA up into dx and dy and then actually do the calculation. Okay, so now if you look at the box on page, what is the time? If you look at the box on page 44 of your handbook, you'll see that formula in the box. The most obvious place to see it is right at the bottom, but it's also present in the integral that's right at the top. So if you just look at the box on page 44, if you don't have your handbook handy, then maybe just make a little note here or look in a friend's. Okay? But notice how if you look in that box on page 44, there's actually quite a few expressions, because I've shown you what it looks like if you actually project it onto one of the other coordinate planes. If you project onto the x, y, okay, so let's have a look. I'm going to say something now that I'm going to repeat many, many times. When you're doing a surface integral, you have to project your surface onto one of the coordinate planes. The choice of which coordinate plane to project onto is incredibly important because it's going to drive everything else that happens in the problem. The choice, every coordinate plane is defined by 2 variables, xy, xz, yz. Those 2 variables are the ones that we differentiate with respect to. So if we're projecting onto xy, then we're differentiating with respect to x and y, which means z has to be the subject, so that we can differentiate z with respect to x and differentiate z with respect to y. If we were projecting onto the xz plane, we would differentiate with respect to x and z, which means y needs to be made the subject. If we project onto the yz plane, then we differentiate with respect to y and z, which means we need to make x the subject. Okay, all right. So that's important. So let's say we choose to project onto the xz plane. Then that means we need to make y the subject, and we're going to do an x and a z derivative. It also means that the d's that go here will be dx and dz. Okay? And our limits of integration will be defined by our region that we've now got on the xz plane. So your choice of which coordinate plane to project onto is incredibly important. And you need to pause and make that decision very carefully and very sensibly before you then begin on all the calculation stuff. Okay. All right. Is there anything else I want to say before I do an example? So what I've done in that box is I've shown you what the conversion factor would look like for all 3 coordinate planes. But obviously it's the same. One more thing that the stuff in the box is reminding me of. Let's say we project onto the xz plane and we have a dx and a dz. It means our integrand can only include x's and z's. It can't include any y's. So everywhere there's a y, we need to replace it by the surface expression. So remember you had to make y the subject in order to do those two derivatives? Well, that thing that y was the subject of, that's going to then go into your integrand to replace any y's that happen to be there. Question?
When you were doing double integrals, the order of integration was important. Does it matter here?
Yes, so the question for the sake of the audio is does the order of integration still matter? And yes, it does. Yes, it does. When you actually carry out the calculation, you write, I'm going to integrate now, what did I differentiate to get this integrand? At that point, you're at a double integral, because you've turned your surface integral into a double integral, and all of those various skills and knowledge that applied for the last few days apply all over again. Did I see a hand towards the back? I thought I did. No, okay. Yeah?
So am I right in thinking we're basically doing like a 3D arc length thing? Yeah, it's like, it seems to be the same, it's like an extension of that thinking.
Yeah, okay, so the reason for that is not so much that we're doing an arc length thing, is that the way I chose to calculate the area, the way I chose to derive this conversion factor was via cross product of vectors getting an area of a parallelogram. There are other ways of achieving this conversion factor that are more to do with Pythagoras' theorem, and are more to do with getting an adjacent side given a hypotenuse. And that, of course, is what we do when we work out arc length. And so there's a geometric in a sense, there's a geometric, what's the word I'm looking for here? Not relationship between, but there's a similarity between the conversion factor here and the conversion factor you have in arc length, because the two can be understood to share a common progenitor of Pythagoras' theorem. If that makes sense. Even though that wasn't the route that I used in this particular derivation. Okay! I hope that was fun. What you need to know is that conversion factor. You don't need to know its derivation. Okay? But I can't give you derivations out of thin air. I can't. That's poor teaching, and you would go away weaker for it. Okay, you are now stronger for it. Don't you feel stronger? You feel stronger? No. Yes, you do. You feel mighty. Question? Sorry, I'm not understanding the question, but maybe it'll come out in some examples. Okay, let's have a look. We have 6 minutes left. That's enough time for... okay, so because projecting... Please, can you keep quiet? Because projecting surfaces onto coordinate planes is an absolutely key skill in doing surface integrals, the way I've constructed the handbook is I've first put in a couple of exercises just doing some projections before we use that in calculations. So, surface integrals, exercise 21, it says, given the surface S projected onto the indicator coordinate plane, sketch the projection with all boundaries and intercepts clearly defined. S is that portion of the parabolic sheet y equals 1 plus 2x squared, I'm going to have to draw that, which lies in the first octant, that's good information, between the planes x equals 0, x equals 2, z equals 4, and z equals 8. All right. Woof, when all that information is going to hit you in the face, and now you need to draw a picture. Okay. Y equals 1 plus 2x squared, and the xy plane, that's a parabola. Okay, but if I turn it into a surface, it's a parabolic sheet. I'm deliberately drawing dotted lines because I know I don't want all of it. Okay. Something like that. All right. It's a piece of a parabolic sheet. I already know I'm only interested in first octant, so I'm not bothering with the side that's behind. X equals 0. Cool. That's the YZ plane. X equals 2. Okay, well, let me make that x equals 2. I tell you what, let me lengthen this axis. Z equals 4 and Z equals 8, so I'm only wanting a piece of this. There we go. I want in that piece. I want in that piece of that parabolic sheet, parabolic gutter, parabolic trough, whatever you want to call it. I want in that little piece of it that's floating in the air. Its far vertical edge is chopped off at the YZ plane. Its closer vertical edge is defined by x equals 2. Its bottom edge is defined by z equals 4, and its top edge is defined by z equals 8. It's bounded by all of those things. Okay, I want to project that onto the xz plane. xz. Okay, you know me, I like to draw my xz plane like this. And if that's surprising you, you've missed some lectures. There you go. So that's my S, that's my R. Of course, you are welcome to do it the conventional way and draw it like, whoops, Daisy, that's not 4, that's X. Of course, you're welcome to draw it like this. That's perfect. I like to draw it this way so that it's a closer analogy to the 3D picture. That's just my personal visual choice. If it bugs you, I understand. I'm still going to carry on doing it, but I do understand if it bugs you. And you are welcome to do that. Okay. There we go. Projecting onto the YZ plane would have been a similar sort of picture, although it wouldn't have touched the Z axis in that case. Okay, we have 3 minutes left. I'm going to say something important. Everybody open your ears. Projecting onto the XY plane is useless. It's useless in the context of surface integrals. There are other ways of approaching it, but in the context of surface integrals, it's useless projecting onto the XY plane because it won't project onto a region. It'll project onto a curve, a piece of parabola. Okay? Now, it's very easy when you're getting flustered and you've shaded the wrong bits and things to project onto the XY plane and make. So here's a mistake that somebody could make. X, Y, here's the parabola. Somebody could say, oh, it's this. Okay, it's not. Okay, because there's nothing to project onto where I've just scribbled. There's nothing to project onto that because there's no surface above it. So that would be a mistake, but it's a very easy mistake to make, particularly when the surface is quite complicated. If you're going to do a surface integral and you project onto a coordinate plane and you make a mistake like that, you think you're getting a region, but you're actually getting a curve. You should become aware of it when you get to the conversion factor. Because think about it, if we were projecting onto the XY plane, we'd be differentiating with respect to X and Y, which means we'd need to make Z the subject. There is no Z in my surface equation. So I would fail at making Z the subject. And at that point, I'd think, what's going on? And then I'd realize, oh, I projected onto a coordinate plane that actually wasn't useful. It didn't actually, I thought it worked, but I was wrong. Question?
So if you have an equation that doesn't have a variable, the plane that you project on has to have that variable in it.
It doesn't have, yes. Basically, look at, the picture is very useful, but the actual equation of your surface is also useful. There is no Z in my surface equation, so I cannot make Z the subject, so I cannot project onto the XY plane. I can project onto XZ, and I can project onto YZ, but not onto XY. Okay, that's a very common mistake for people to make, to project onto a coordinate plane, think that you're getting a region when you're actually getting a curve. And then later on, if you discover, oh, hold on, I can't actually make Z the subject, don't think, oh gosh, I'm just useless at conversion factors, I'll just fudge something. Take that as an indicator that your projection actually was illegitimate to begin with and go back and project on somewhere else. Okay, I'll stop there. There is a part B. I'll do that on Monday, or maybe I'll give it to you to do, and you'll do number 22, and then we'll move on with some actual calculations.